3. All right, everybody. So today we're talking about inverse functions. I briefly mentioned them yesterday, and I guess I should give them some sort of definition, but inverse, inverse functions. I guess I'll just summarize it real simple. Undo one another. All right. So we've heard of inverse operations when we've been solving equations, right? If I have x plus 1 equals 0, instead of adding 1, we use the inverse operation of addition, which was subtraction. And you'd like subtract 1 from both sides, right? That was an inverse operation, right? Addition, subtraction, undo one another. Multiplication, division, undo one another, right? Square rooting and squaring, undo one another, right? So inverse functions are going to be two functions that undo one another. Officially speaking, I guess, in terms of, well, got the blurries. Whenever I see like blurry, it always reminds me of like playing The Sims when The Sims get all blurry. I don't know if anyone knows what I'm talking about. No? Yeah. They got the blurries. So let's see. Here we go. Paste. And so you don't have to necessarily write down this whole thing. Actually, you don't. I don't think you even necessarily have to write this down, but it's worth looking at. So definition of inverse functions. Two functions f and g are inverse functions if and only if both of their compositions are the identity function. Identity function basically is the function that doesn't do anything. So like if I have a function that's just equal to x, whatever you input gives it back as an output, right? Doesn't do anything. So, and we saw that a little bit yesterday when we were looking at that. So basically, f of g of x, f will undo what g did and just give us x back. G of f of x, g will undo what f did and just give us x back. So, I guess a quick example of this. If I have the function f of x equals, let's say 3x plus 1. I guess maybe we could have some interesting conversation here. What do you think an inverse function of that would be? Let's get some guesses in here. Take a moment to think about it. What would undo what f is doing here? All right, so here's one option, 1/3 x minus 1. Any other guesses? Or let me ask, what does the function f do, specifically to x? What does it do in what order? Let's say, step 1, what does f do to x? Order of operations. It multiplies by 3. And then what happens to that? Adds 1. What happens in this function? Right, divides by 3. And then subtracts 1. However, the thing that's a little bit sneaky here, because I happen to throw two operations at us right off the bat, is the order. I kind of have to undo what f did in order. Okay? So the first thing that would have to happen to x isn't the dividing by 3. I'll have to deal with this adding 1. So I have to kind of undo it backwards, right? Disassembling a bomb style, right? So what's the inverse of adding 1? Subtracting 1. And then after I've done that, I have to do the inverse of multiplying by 3, which is dividing by 3. So I could represent that like this or like this. So I know it's just a subtle difference, so there's a really good, right, that by instinct, that's exactly what I would have said as my first guess as well. But yeah, so in this case, though, we also not only have to undo the operations, we have to undo them in kind of the reverse order. Okay? So our actual g of x will be this one here. And what this is claiming is that f of g of x should equal x. So let's verify that, shall we? Let's figure out what is f of g of x. So the function f is 3 times something plus 1, right? And what is that something going to be? in this case, the function g. So I'll have this 1/3 times x minus 1, or whichever way you would have decided to write that. So let's simplify this. What happens? What can I do? Ideas? You could, yeah, you could. You could distribute that and then distribute this 3 after it to whatever the answer is. But notice I can actually multiply these two right off the bat. What is 3 times a third going to be? Notice what color I'm using. Right? These are going to... Right? You're not wrong for saying distribute the 1/3. That would have also worked. All right, so I just want to point that out. So I'd have x minus 1 and then plus 1. And I think you guys agree -1 plus 1 is 0. So I just get regular old x, which is what I wanted, right? F of g of x should equal x. However, it also has to be true in the other direction. F has to be the inverse of g. Or no, g has to be the inverse of x, my bad. So g of f of x, let's see if I can fit it right here on the side. It might be a little snug, but they'll be cozy. So let's see. So here's g of x. So it's 1/3 times the difference of whatever I have and 1, right? So what's going in those parentheses? The function f. So 3x plus 1. And I guess in this case, I can't really do my 1/3 trick just yet. When I simplify this, I can drop those inner parentheses and the 1s would cancel out, right? So I would have 1/3 times 3x. And I think you guys agree that 1/3 times 3x is just x. So it turns out that, in fact, g is the inverse of f, right? F is the inverse of g, so they are inverse functions of one another. Okay? Let me show you graphically what's going on here. So let's look at the function f. So this was kind of an algebraic analysis of inverse functions. Graphically, there's going to be this interesting relationship between them as well, in which, so let's graph f of x and g of x. So for f of x, this might be bringing us back a ways. I guess I'll write it down. F of x equals 3x plus 1. Does anyone have any idea what information they could pull from this equation that would help us graph? We haven't done much with these kinds of graphs. It's going to start at 1. That's our y-intercept. Goes up by 3 over 1, so the slope, symbolized by the variable 3, is our slope, right? For function g of x, I'm going to have to do a little bit of work to it. It was 1/3 times x minus 1 in parentheses. So that's the same as 1/3 x minus 1/3 if I distribute that 1/3. So what is my slope and y-intercept in that case? It's not as nice, but we'll still accept it.
-1/3.
Right, so that's the value of b, the y-intercept. And the slope? Positive 1/3. And just to connect this to our parabolas as well as our polynomial functions, notice that my constant happens to be my y-intercept, right? And that was also true with parabolas. The c term in a parabola was the y-intercept, or the constant term in a polynomial function was our y-intercept. So just some consistency across the board there in the things that we've learned. So let me see if I can actually graph these any good. 1, 2. let's see, I'm going to have to go up as high as 4 here. 3 and 4. 1, 2, 3, and 4. I don't have to go down as far. 2, 3, 1, 2, 3. So let's try graphing f of x. I'll make f of x the green function. So y-intercept of 1 and a slope of 3. So that means I go up 3 units and over 1, right? And draw my line. I wonder. I never ever used this toolbar. Let me just try the line tool for once. Blam. Wow, what do you know? That works out. Kind of nice. And then for g of x, I'll make that my, I don't know, I guess orange line. The y-intercept's a little bit uglier. It's 1/3, so if I divide this into negative 1/3, sorry. So there's my y-intercept there. And the slope is 1/3, so how do I do that?
Up 3 over
Come in.
1.
Up. No, not up 3 over 1. Hi. Yeah, go right ahead.
2 seconds.
Yep, take your time. So up 1 over 3 would work. However, I'm kind of on like this weird little negative 1/3 mark. So if I go up 1/3, 2/3, 3/3, that's a full unit. And then over, wait a minute, over 3, right? Yeah. So this is like at the point 2/3, no, sorry, at 3 comma 2/3 is where that point is. Another way you could do this is a little bit weirder. I could go up 1/3, which would bring me to the x-axis, and over 1. And that would land on the same line. So let me see if I can use my line tool here. Let's see if I can actually plan this ahead. Nope. Let's see. That's pretty good. I'm happy with that. I hit all 3 points, kind of. Blam. And so that's what we got for our 2 lines. Now, it turns out if my graph was more to scale, and if these functions were fancier, we'd have some more interesting relationships that you could tell from them. But I'm going to give away the key relationship between these. It turns out if I was to graph the line y equals x, I think I can get rid of this guy now. So here's the line y, nope, that's not the color I wanted. Here's the line y equals x, which is basically passes through the origin. It's kind of like a 45-degree angle. It turns out that these 2 lines, since they are inverses of one another, are mirrored over the line y equals x. All right? Kind of crazy. A little bit crazy. So it means that this point here at 1 comma 4 on this line will be the point 4 comma 1. And it actually is. And this point here at 0 comma 1 on the orange line will be 1 comma 0. All right? And it actually lines up. And this point at negative 1/3, sorry, at 0 comma negative 1/3 will be at negative 1/3 comma 0. And then there's even this point where you can actually see they cross all 3 lines and they work out. So inverse functions are mirrors of one another over the x. No, over the line y equals x, sorry. There we go. So watch this. So if that means I could give you a function graphically. Example, that's good enough. Graph the inverse. So watch this. So I'm just going to draw a quick little swoop. Nope, that's terrible. Yep. Yep. That's a little better. And let me draw an original graph. So what if my original graph looked like this? What if it was like, I don't know, something like that. All right. So there's my original function. And if I want to graph its inverse, so here's, I'll call this f of x. to graph its inverse, and if I was just doing this purely graphically, the way I would do that is draw the line y equals x, and I'm going to mirror it over that line. Okay, so it'll be a little bit tricky here, but let's do it. So, so here's this point, mirror it over the line. There'd be a point right here, I guess. Here's this point, right? It's kind of that far away from the line, so mirrored over here would be kind of right here. So I guess this piece would look like, well, something like this. All right. Here's this point, so that would be kind of mirrored there. This point would be mirrored over here. So I think this would look like this. Something like so. Let's see. Let's grab this point. Looks like a good one. So if I mirror it over the line, mirroring means it's going to be equidistant from the line and, you know, kind of perpendicular to it is how I'm mirroring it. So a little bit tricky, but yeah, it's going to be right over here. Something like that. And then this point is kind of like this far away over here. So, and then it goes around like that-ish. Right? And this would be the inverse of f of x. And by the way you can write that is f to the -1 of x. And it's never read. You'll never hear me say that again, unless you were to rewind and watch this video. That is read as f inverse of x. Okay? So that little to the -1 symbol means inverse, literally. All right? And yeah, so you can kind of find all sorts of crazy functions and mirror them. Now, one of the things I want to point out, yesterday we talked about the vertical line test, and that a graph is not a function if it doesn't pass the vertical line test. Does anyone remember that? Could they summarize that maybe for me? Like, what was the vertical line test?
If you were to draw a vertical line through the graph, the line cannot touch more than one point.
Right. So notice my green function. If I draw multiple vertical lines, it's hitting only ever at one point, no matter which vertical line I draw. Okay? So f of x is in fact a function, all right, because of that. However, this orange graph isn't a function because there's, look at just the y-axis right here. I'm hitting 1, 2, 3 points on it. So it turns out inverses won't necessarily themselves be functions, okay? Because it might fail something like the vertical line test. And that's okay, all right? So, and by the way, when it's not a function, it's just called a relation. So it's kind of like a relationship between x's and y's, where this one is a function because it passed the vertical line test, all right? So relations have less stipulations or rules on them compared to functions, where functions have to have exactly one output for every input. And when we talk about relations, I mean, eventually we'll be talking about graphs of circles and ellipses and hyperbolas, you know, that all sorts of things that don't pass the function test. And then we'll actually even someday be talking about like weird spirals. I think that's the spiral of Archimedes, stuff like that. All sorts of crazy stuff. So there's interesting things that happen in the world of relations, but most of the time, for now, we'll just deal with functions. All right. So far, I mean, I've talked about how to find an inverse graphically, and we know what an inverse looks like algebraically, but I think you guys agree it was kind of at least a little bit weird having to figure out what that would have been. And if I have an even more complicated function, it would be even harder for us to find it. So let me find a good one. I like it a lot. Here we go. I think actually I'll do it over here on the top right of my page. So let's talk about how you can find the inverse algebraically. All right. I'm going to teach by example, I guess. So find f inverse of x. All right. So suppose f of x is x squared. Let's do this plus 4. And I'm going to give you some steps for this. Okay. So let's see. Step 1 will be replace f of x with, nope, with y, not, I don't know what I wrote, witty almost, without a t, I'm not sure, with y, all right? So for us, what that means is I will write this as y equals x squared plus 4, right? Step 2 will be switch x and y. And think about the fact that function inverses, right, graphically are mirrored over the line y equals x, right? That's literally switching the x and y. Remember when I had the point 1, 0, it was 0, 1 on the other? I was switching the x and y coordinates between a function and its inverse. That's kind of why this is happening, all right? So functions and inverses, they switch x and y. And then step 3 will be solve for new y. So let's do, I guess I should do some of these steps out. So when I switched x and y, this would be x squared, nope, x equals, sorry, y squared plus 4. And now how could I solve that for y? What would I do to get y by itself here? Eventually, but I'd have to deal with the 4 first. So I'll have x minus 4 equals y squared. And now I can root both sides. And am I forgetting anything? Plus or minus, yeah, don't forget it. That's right. Plus or minus, don't forget it. So I'm going to, and then just switcheroo this. So I'll get y equals plus or minus the square root of x minus 4. All right? And then the last step will be rewrite y as f inverse of x. So this is f inverse of x is equal to plus or minus the square root of x minus 4. And algebraically, we have now found an inverse function. So not too shabby. And you can follow this process no matter what they happen to be. Now some of them might be, trickier to solve or different things like that, but let me actually open up. I'm going to graph the function and its inverse just so you can see what's going on here. So let's see. So my original function was what? X squared plus 4? Or yeah, plus 4, right? So I'm going to graph this on this here, and you see, yep, it's a handy-dandy parabola, right? I guess I could make that a little line style medium. Sounds good. There we go. So there's my function, right? And to graph its inverse, we are theorizing that its inverse, unfortunately, yes, bless you, the inverse is going to come in 2 parts. I believe square root, yeah, I have to use this weird notation here, of x minus 4. All right, I'm going to have to graph the positive version of this and then the negative version of it. And you'll see why in a moment, but here's the positive version. Okay, let's see, line style, medium, line color. I'll make it naranja again there. There we go. So you can see that the plus version of this square root is just kind of like the top half of this sideways parabola, right? So that's kind of interesting. And then I think you guys can imagine that the negative version would be negative square root of x minus 4. Enter. And that gives me the bottom half of that sideways parabola. So in this case, like I said, it's possible for your inverse not to be a function, right? This would definitely not pass a vertical line test. And just to make things clear, let's graph the line y equals x. And you can see line style, medium, line style. Let's make it dashed, and I'll even make it color there. So you can see that these are, in fact, mirrors of one another over that line, right? So a thing of beauty right there. I might even grab a snapshot of this. But yeah, so the plus or minus actually had to account for the fact that it couldn't be graphed without breaking it into two parts. So the top half of this was a function, and the bottom half was a function, but together they could only be a relation because they'd fail the vertical line test. So, and with that graph, oh no, there we go. All right. So with this graph, you can see a little bit more clearly. So here's f of x, and here's f inverse of x. And since it has a better, accuracy graphing than I do, I think the mirroring is a little bit more clear, right? So, thing of beauty. So that's the idea of inverse functions, understanding them graphically, algebraically, stuff like that. If I had a set of ordered pairs, right? If I said f of x is 1, 2, and 3, 4, and 5, 6, its inverse would just switch all of those ordered pairs. So it'd be 2, 1, right? And 4, 3, and 6, 5. So all of our representations of functions, all you really have to do is switch the x and the y, is kind of the big idea for inverses. All right? So thank you, ladies and gentlemen.